Hello there, and welcome to Simple Sleepy Science. Tonight, we're exploring the quiet miracle happening right now, in this very moment, as your eyes move across these words. Your eyes are making millions of tiny movements every single second. Each blink paints a new picture. Each glance captures light that's been traveling for billions of years. And somehow, your brain turns all of this into the world you see. It's happening right now. You're doing it without even thinking about it. This is your place for calm curiosity. So, settle in, get comfortable. Let's explore the peaceful science of how you see. We begin with something simple. Something you've done thousands of times today already. Your eyes blink about 15 times every minute. That's roughly 20,000 times a day. But here's what makes it beautiful. Each blink is like a tiny reset button, a moment of darkness that your brain erases from your memory. You never notice the blackness. Your mind fills in the gap with a continuous stream of sight. Think about that for a moment. Every time your eyelids close, your world goes dark. But you don't experience 20,000 moments of darkness each day. You experience one smooth, unbroken view of the world around you. Your brain is so good at editing out these gaps that you've probably never even thought about it until right now. If this quiet journey through the science of sight brings you peace, consider subscribing to join our community of calm learners. And leave a comment below. Where are you watching from tonight? What time is it there? We'd love to know. It's one of your body's most patient kindnesses, keeping your world smooth and unbroken, even as your eyelids close and open again and again. The blink itself takes about 1/10 of a second. That's faster than you can snap your fingers. And in that tiny moment, your eyes get exactly what they need. Each blink spreads a thin layer of tears across your eye. These tears aren't the kind you cry when you're sad. They're a special mixture that keeps your eyes healthy. They wash away dust and tiny particles. They deliver oxygen to your cornea. They keep everything smooth and clear. Without blinking, your eyes would dry out in minutes. They'd become scratchy and uncomfortable. But you blink so naturally, so automatically, that your eyes stay comfortable all day long. Your eyelids move with surprising precision. The upper lid does most of the work, sweeping down quickly and then lifting back up. The movement is controlled by some of the fastest muscles in your body. These muscles never get tired the way your leg muscles do after a long walk. They're built for this endless, rhythmic work. Even while you sleep, your eyes continue their work in different ways. But during your waking hours, blinking protects your vision without you ever having to think about it. It's a small gift your body gives you thousands of times each day. A momentary rest that feels like no rest at all. And it prepares your eyes for what they do best. Capturing light from the world around you. Light bounces off everything around you. Your coffee cup, the wall, the screen you're reading this on. And that light carries information, color, shape, distance. Your eyes catch that light through a tiny opening called the pupil. It's the black circle in the center of your eye. And it's far more clever than it looks. Think of your pupil like a doorway. When it's dark, the doorway opens wide, letting in as much light as possible. When it's bright, the doorway closes smaller, protecting the delicate structures inside. This happens automatically. You never have to think about it. Your pupils are constantly adjusting to help you see clearly, no matter where you are. The colored part around your pupil is called the iris. It's made of tiny muscles that control how big or small your pupil gets. In very dim light, your pupil can open to about 8 millimeters wide. That's roughly the size of a pencil eraser. In bright sunlight, it shrinks down to about 2 millimeters. Just a tiny dot. This change can happen in less than a second. Your pupils respond to more than just light. They also respond to your emotions. When you see something exciting or interesting, your pupils get slightly bigger. When you're concentrating hard on a problem, they expand. Scientists have used this to study how people react to things. Because your pupils give away what you're thinking before you even speak. The pupil isn't actually a hole in your eye, though it looks like one. It's an opening through the iris that leads deeper into your eye. Behind it sits a clear, curved structure that does the real work of vision. But the pupil's job is essential. It controls exactly how much light reaches that inner world. In darkness, your pupils open so wide they can let in over 16 times more light than when they're closed tight in brightness. This range is remarkable. It means you can see in the soft glow of candlelight and in the harsh glare of a summer day. Your pupils make both possible by adjusting constantly, smoothly, without any effort from you. Watch someone's eyes when they walk from a dark room into sunlight. You'll see their pupils shrink almost instantly. It's your body protecting itself. Too much light at once can be uncomfortable, even painful. But your pupils react so fast that you barely notice the change yourself. You just keep seeing clearly. This adjustment happens in both eyes at the same time, even if only one eye is exposed to light. Cover one eye and shine a light at the other. Both pupils will shrink together. Your brain coordinates them perfectly. It's another small example of how your visual system works as one complete unit. Right now, as you read this, your pupils are set to exactly the right size for the light in your room. They've been adjusting all day, every moment, keeping the amount of light entering your eyes just right. And they'll keep doing this work as long as you're awake, preparing that light for the next step of its journey into your eye. Behind your pupil sits a clear lens. It's about the size of a small candy, shaped like a disc that's thick in the middle and thinner at the edges. And it's one of the most hard-working parts of your body. This lens bends and flexes thousands of times a day, changing shape to focus on things near and far. The lens is held in place by tiny fibers, almost like strings on a guitar. These fibers connect to a ring of muscle that surrounds the lens. When you look at something close, like your phone or a book, those muscles tighten. The fibers loosen, and the lens becomes rounder, more curved. This stronger curve bends light more sharply, bringing close objects into focus. When you look at something far away, like a bird in the sky or a distant mountain, the opposite happens. The muscles relax, the fibers pull tight, and the lens flattens out. This gentler curve is perfect for focusing on things far from you. The change happens so smoothly, you never feel it. You just see clearly, whether you're looking at your hands or at the horizon. This process is called accommodation. Your lens has been accommodating for you since you were born. Every time you shift your gaze from near to far, your lens reshapes itself. It happens hundreds, maybe thousands of times each day, and it does this work without ever complaining, without ever needing rest. The lens itself is completely clear. No blood vessels run through it. No nerves either. It's made of special proteins arranged in such precise patterns that light passes through without scattering. These proteins are organized like layers in an onion, each layer slightly different, but all working together to stay transparent. It's one of the clearest biological materials in your body. Your lens grows throughout your entire life. New layers of cells form on the outside, pushing older layers toward the center. The very center of your lens contains cells that formed before you were born. They've been with you from the beginning, still clear, still working. The lens gets slightly larger and slightly less flexible as you age, but it never stops doing its job. When you're young, your lens is remarkably flexible. A child's lens can change shape dramatically, allowing them to focus on something just inches from their nose. As decades pass, the lens becomes firmer. The proteins inside it become denser. This is why many people need reading glasses as they get older. The lens still works, but it can't curve quite as much as it once did. But even with these changes, your lens remains extraordinary. It adjusts to every distance you look at, from the words on this page to the ceiling above you, to the view outside your window. Each shift in focus requires a different shape, and your lens provides it. Patiently, precisely, automatically. Right now, your lens is focused on these words. It's curved just enough to make the letters sharp and clear. And when you look up, it will flatten slightly, ready to show you whatever lies in the distance. This quiet, constant work continues every waking moment. After light passes through your lens, it travels deeper into your eye. It crosses through a clear gel that fills most of your eyeball, and then it reaches the back wall. This is where the real magic happens. This is where light becomes sight. At the back of your eye is a thin layer of tissue called the retina. It's about as thick as a few sheets of paper stacked together. But this delicate layer contains over 120 million special cells. These cells do one simple job. They catch light, and when light hits them, they send messages to your brain. The retina lines the inside of your eyeball like wallpaper lines a room. It curves along the back, covering an area about the size of a large postage stamp. Every part of this small surface is packed with light-catching cells, all working together to capture the image your lens has focused. These cells are called photoreceptors. The name tells you what they do. Photo means light. Receptor means something that receives. They receive light and respond to it. Each cell contains special proteins that change shape when light touches them. This shape change triggers an electrical signal, and that signal starts a message on its way to your brain. The retina doesn't just catch light randomly. It's organized in layers, each doing a specific job. The photoreceptors are at the very back, pressed against a dark layer that absorbs extra light. In front of them are connecting cells that gather signals and begin processing them. Then come cells that fine-tune the messages, making them clearer and more useful. By the time information leaves your retina, it's already been organized and refined. Your retina works in the brightest sunlight and in the dimmest moonlight. It adapts to help you see in almost any condition. In bright light, some of its cells become less sensitive, protecting themselves from too much stimulation. In darkness, other cells become incredibly sensitive, able to detect even the faintest glow. The retina never stops working. As long as light reaches your eye, your retina is catching it and turning it into signals. Right now, every word you read is being translated by millions of cells firing in patterns. Each letter creates a unique combination of active cells. Your retina is reading before your brain even interprets the meaning. What's remarkable is how consistent this process is. The same light hitting the same spot will trigger the same cells in the same way every single time. This reliability is what lets you trust your vision. A blue sky looks blue today and will look blue tomorrow because your retina responds to that wavelength of light in a predictable way. The retina is fragile, but incredibly durable. It can last a lifetime without replacement. The cells that caught light when you saw your first sunrise are still working now, still faithfully translating the world into signals. They've captured countless images, millions of faces, scenes, moments, and they continue this work without pause, turning every photon that reaches them into a message your brain can understand. Your retina contains two kinds of light-catching cells. They have simple names, rods and cones, and they do very different jobs. Rods are your night vision helpers. You have about 120 million of them spread across your retina. They're shaped like tiny rods, which is how they got their name. These cells are incredibly sensitive to light. They can respond to just a few photons, the smallest units of light that exist. This makes them perfect for seeing in darkness. But rods have a limitation. They can't detect color. They only tell you about brightness and darkness, light and shadow. When you're in a dark room and everything looks gray, that's your rods at work. They're showing you shapes and movement, but not colors. It's like watching an old black and white movie. Cones are your color experts. You have about 6 million of them, mostly concentrated in the center of your retina. They're shaped like small cones, wider at one end than the other. Cones need more light to work than rods do. This is why colors fade when the sun goes down. Your cones need brightness to function properly. You have 3 types of cones. Each type responds to a different wavelength of light. One type catches short wavelengths, which you see as blue. Another catches medium wavelengths, which you see as green. The third catches long wavelengths, which you see as red. These 3 types working together create every color you've ever seen. When light hits your eye, it activates different combinations of these 3 cone types. A yellow flower activates both your red and green cones. A purple sunset activates your red and blue cones. Your brain reads these combinations and creates the experience of color. Millions of possible shades from just 3 types of cells. The center of your retina, called the fovea, is packed almost entirely with cones. This small spot, about the size of a pinhead, is where your vision is sharpest and colors are most vivid. When you look directly at something, you're pointing your fovea at it. This is why colors look brightest when you stare right at them. Rods are arranged differently. They're spread throughout your retina, but are most concentrated away from the center. This is why you can sometimes see faint stars better when you look slightly to the side of them. You're using the rod-rich areas of your retina, which are more sensitive to dim light. Together, rods and cones create everything you see. The sunset, painted in orange and pink. The stars scattered across a dark sky. The face of someone you love lit by candlelight. All of it comes from just two types of cells responding to light in their own specialized ways. Right now, as you read these words, your cones are active, showing you the colors and details of the text. Your rods are monitoring the darker areas around the edges of your vision, ready to alert you if something moves. Both types work constantly, each contributing their unique abilities to create your complete view of the world. Once your rods and cones catch light and create signals, those messages need to reach your brain. This is where the optic nerve comes in. It's the pathway that connects your eye to your mind. About 1 million nerve fibers bundle together at the back of each eye, forming the optic nerve. If you could see it, it would look like a cable about as thick as a pencil. But inside that cable is an incredible amount of information traveling at remarkable speeds. Every signal from every photoreceptor in your retina funnels into this nerve. Millions of messages every single second. Bright spots, dark areas, red hues, blue shades, movement to the left, stillness in the center. The optic nerve carries all of it, organizing the chaos into streams of data your brain can process. The speed is astonishing. Signals travel along the optic nerve at about 200 miles per hour. That's faster than a race car. This means you see things almost the instant they happen. A ball thrown toward you. A smile spreading across someone's face. A bird taking flight. The delay between the event and your awareness of it is so small you never notice it. The nerve fibers in your optic nerve are wrapped in a special coating called myelin. This coating acts like insulation on an electrical wire. It helps signals move faster and prevents them from interfering with each other. Without myelin, your vision would be slower and less clear. Messages would get mixed up along the way. Your optic nerve isn't just a passive cable. It does some processing of its own. Cells in your retina have already begun organizing the information, grouping similar signals together and highlighting important changes. By the time signals enter the optic nerve, they're already more than raw data. They're structured messages ready for your brain to interpret. The optic nerve travels from the back of your eye through a small hole in your skull. This opening is just big enough for the nerve to pass through. Then it continues inward, carrying its precious cargo of visual information to the back of your brain, where your visual cortex waits to receive it. Each eye has its own optic nerve, but these two nerves don't stay separate for long. They meet at a point called the optic chiasm, where some of their fibers cross over to the opposite side of your brain. This crossing is why damage to one side of your brain can affect vision in both eyes. Your visual system is interconnected in complex and efficient ways. The optic nerve works constantly. As long as your eyes are open and light is entering them, signals are flowing through this nerve. It never gets a break during your waking hours. It's been carrying messages since you first opened your eyes as a patent newborn, and it will continue this work for as long as you live. Right now, words on this page are being translated into electrical pulses and sent through your optic nerves to your brain. The information highway is busy, carrying the shapes of letters and the colors of the background, all at incredible speed, so you can read and understand without any conscious effort. Where the optic nerve connects to your retina, something strange happens. There's a spot where no rods or cones exist. The nerve fibers need space to exit your eye, and at that exact location, there are no light-catching cells at all. This means you have a blind spot in each eye, a small area where you literally cannot see. It's about the size of a large grape if you could project it onto a wall at arm's length. And you've had this blind spot your entire life without ever noticing it. The reason you don't notice is remarkable. Your brain fills in the gap. It looks at what's around the blind spot and makes an educated guess about what should be there. If you're looking at a blue wall, your brain paints blue into the blind spot. If you're looking at a pattern, your brain continues that pattern. The filling in happens so automatically and so perfectly that you never see the gap. You can find your blind spot if you try. Close your right eye and look at a spot on the wall with your left eye. Hold your thumb out at arm's length, slightly to the right of where you're looking. Slowly move your thumb to the right while keeping your eye fixed on the original spot. At some point, your thumbnail will disappear. It's entered your blind spot. Move it a bit further, and it reappears on the other side. But even when you find it this way, you don't see a black hole or an empty space. You see whatever your brain has decided should be there based on the surrounding area. If your thumb is against a white wall, the spot where it disappears looks white. Your brain is actively constructing your view, not just receiving it. This happens in both eyes, but your blind spots are in different locations for each eye. What the left eye can't see, the right eye usually can, and the other way around. When both eyes are open, they cover for each other. This is another reason you never notice the gaps. Your vision from two eyes overlaps in ways that hide the missing pieces. The blind spot exists because of how your eye is built. The retina developed in a way that puts the light-catching cells behind the nerve cells. So the nerves have to pass through the retina to exit the eye, creating this small area without receptors. Some animals, like octopuses, have retinas built the opposite way. Their photoreceptors are in front, and they don't have blind spots at all. But your blind spot isn't a flaw, it's a trade-off. The way your retina is organized gives you other advantages, and your brain compensates so well that the blind spot effectively doesn't exist in your daily experience. You've lived with it forever and never felt like anything was missing from your view. Your brain's ability to fill in this gap shows how much of vision happens in your mind, not just in your eyes. Seeing isn't passive. Your brain actively constructs what you see, making assumptions and filling in missing information to create a smooth, complete picture of the world around you. Here's something strange about how your eyes work. The image that hits your retina is upside down. Everything you look at enters your eyes flipped. The ceiling appears at the bottom. The floor appears at the top. Left and right are reversed too. This happens because of how lenses work. your lens is curved. When light passes through a curved lens, it bends. The light from the top of an object bends downward. The light from the bottom bends upward. By the time these light rays reach your retina, they've crossed over each other. The result is an inverted image. You can see this same effect with a magnifying glass. Hold it up and look at something far away through it. The image will appear upside down. Your eye's lens does exactly the same thing. Every moment of every day, the world projects onto your retina upside down and backwards. But you don't see it that way. Your brain flips it back. This correction happens so early in the processing that you never experience the upside down version. By the time you become aware of what you're seeing, your brain has already set everything right side up. The correction is so complete and so automatic that even knowing about it doesn't let you see the original inverted image. Scientists have done experiments with special glasses that flip everything you see. People who wear these glasses see the world upside down at first. Walking and reaching for objects becomes difficult because their vision doesn't match what their brain expects. But after a few days, something amazing happens. The brain adapts. It starts flipping the image again, and suddenly the upside-down world looks normal. When the glasses come off, everything looks upside down again for a while, until the brain readjusts. This shows how flexible your brain is. It doesn't care whether the image on your retina is upside down or right side up. It just cares about making sense of the information. Your brain has been flipping images since you first opened your eyes as a baby. Back then, you had no concept of up or down anyway. Your brain simply learned to interpret the signals from your retina in a way that matched your other senses. When you reach for something, your hand goes where you expect it to. When you walk toward a door, you move in the right direction. This only works because your brain has created a consistent internal map. It doesn't matter that the raw data comes in upside down. What matters is that the interpretation is reliable and useful. Your brain performs this flip for both eyes simultaneously. The two upside-down images from your left and right eye get corrected together, then merged into one view. You experience a single right-side-up world, even though both retinas are receiving inverted images. This correction has been happening every moment since birth. Every face you've seen, every word you've read, every sunset you've watched, all of it came into your eyes upside down. And your brain quietly, instantly, turned it right side up before you could notice. It's another invisible gift your visual system gives you, working behind the scenes to make seeing feel effortless. Your eyes don't see the way a camera takes a picture. A camera captures everything in its frame at once. Your eyes work differently. They jump from point to point, grabbing small pieces of information and letting your brain stitch them together. These jumps are called saccades. Your eyes make 3 to 4 of them every second. Each saccade is incredibly fast, lasting only about a 20th of a second. During the jump itself, your vision blurs, but your brain edits out this blur. You never see the motion. You only see the clear views before and after each jump. Right now, as you read this sentence, your eyes aren't moving smoothly across the words. They're jumping. They fix on one word, stay still for a fraction of a second, then jump to another word. You might think you're seeing all the words at once, but you're actually seeing them in quick snapshots that your brain assembles into a continuous experience. Your eyes jump to whatever seems important: a face in a crowd, a movement at the edge of your vision, the next word in a sentence. Your brain decides where to look next based on what matters. And this happens so fast and so automatically that you feel like you're choosing where to look. But much of it is your visual system making rapid decisions for you. Between saccades, your eyes stay remarkably still. This stillness is when you actually see clearly. Your fovea, that tiny spot packed with cones, points at whatever you're focusing on. The rest of your vision fills in around it. But only that central point is truly sharp. Everything else is less detailed than you think it is. Your brain does something clever with this limited information. It takes the sharp details from your fovea and combines them with the blurrier information from the rest of your retina. Then it fills in gaps, using memory and expectations. The result feels like a complete, detailed view of everything around you. But most of what you think you're seeing is actually your brain's best guess. You can test this. Look at a word in the middle of this sentence. Without moving your eyes, try to read the words at the beginning and end of the sentence. You'll find they're much harder to make out. They're blurry, less defined. But when you were reading normally, jumping from word to word, every word seemed equally clear. That's your brain constructing a complete picture from incomplete information. This system is efficient. Your brain doesn't need to process every detail of every object in your view. It focuses processing power on what matters and fills in the rest. This is why you sometimes miss obvious things. If your eyes never land on something, your brain might assume it's not there and fill in that space with background. Your visual world is being built in real time, moment by moment, from quick glances and educated guesses. Yet, it feels solid and complete. It feels like you're seeing everything all at once. This seamless construction is one of your brain's most impressive achievements, happening constantly without any effort from you. Color doesn't exist in the world the way you think it does. Objects don't actually have color. They have surfaces that reflect certain wavelengths of light. And it's your brain that turns those wavelengths into the experience of color. Light is made of waves. Different wavelengths create different colors. Short wavelengths become blue in your mind. Medium wavelengths become green. Long wavelengths become red. But these wavelengths themselves aren't colored. They're just energy moving through space. Color is your brain's invention, a way of organizing light into something useful and beautiful. When you look at a ripe tomato, its surface absorbs most wavelengths of light, but reflects the longer ones. Those long wavelengths enter your eye and activate your red sensing cones. Your cones send signals to your brain, and your brain creates the sensation you call red. The tomato isn't red. Your experience of it is red. This might seem like a small distinction, but it's profound. Color exists only in your mind. Two people looking at the same tomato are both having the experience of red. But we can never know if your red looks the same as someone else's red. We've all agreed to call that sensation red, but the actual inner experience might be different for each person. Your brain combines signals from your 3 types of cones to create every color you've ever seen. Orange isn't a wavelength your cones can detect directly. Instead, it's what your brain creates when your red and green cones activate together in certain proportions. Purple works the same way, mixing red and blue signals. Yellow comes from red and green. Every shade, every hue is your brain mixing and interpreting signals. This mixing can create colors that don't exist in the rainbow. Brown, for instance. There's no brown wavelength of light. Brown is what your brain makes when you see orange next to darkness. It's a color that only exists in context, created entirely by your visual system. The same physical wavelength can look different depending on what surrounds it. A grey square on a white background looks darker than the same grey square on a black background, even though they're reflecting identical wavelengths. Your brain adjusts colours based on context, trying to figure out what objects really are, rather than just what light they're reflecting. Even white is an invention. When all 3 cone types activate equally, your brain interprets this as white. But sunlight contains all colours mixed together. A white shirt in sunlight and a white shirt in candlelight reflect very different wavelengths, yet both look white to you. Your brain compensates for the lighting, maintaining colour consistency across different conditions. The sunset you watched last week, painted in orange and pink, was your brain's interpretation of light scattering through the atmosphere. The blue sky above you is your mind's response to short wavelengths dominating the scattered light. Every colour that has ever moved you, brought you joy, or caught your attention was created inside your head from simple wavelengths of electromagnetic energy. Colour is your brain's gift to you, a way of experiencing light that goes beyond mere wavelengths, turning the physical world into something vivid and meaningful. Not everyone experiences colour the same way. About 1 in 12 men and 1 in 200 women have what's called colour blindness. But the name is misleading. Most people with colour differences aren't blind to colour, they just see it differently. The most common type affects how people see red and green. These 2 colours might look similar, like different shades of brown or grey. This happens when one type of cone doesn't work as it should. The red sensing cones and green sensing cones are very similar genetically. Sometimes one type doesn't develop properly or works less efficiently than usual. Imagine looking at a field of grass with red poppies scattered through it. Someone with typical colour vision sees bright red flowers standing out against green grass. Someone with red-green colour differences might see the flowers as darker patches that blend more with the grass. The flowers don't disappear, but they don't pop out the same way. For most people with colour differences, the condition is inherited. The genes that control cone development are located on the X chromosome. Men have only one X chromosome, so if that chromosome carries the variant gene, they'll have colour differences. Women have 2 X chromosomes, which usually means one can compensate if the other carries the variant. Many people with colour differences don't realise they see differently until someone points it out. If you've seen the world a certain way your entire life, that's just what the world looks like to you. It's normal. A person might learn in school during a color vision test that they mix up certain colors, but until that moment, they had no reason to think their experience was different from anyone else's. Some people are missing 2 types of cones instead of 1. This is rarer. They see the world mostly in shades of blue and yellow, or even more rarely, in shades of brightness without much color at all. Their world isn't less interesting, it's just organized differently. They notice contrasts and patterns that others might miss. Scientists have even found a few women who have 4 types of cones instead of 3. These tetrachromats can potentially see more color distinctions than most people. Where you see one shade of red, they might see subtle variations. Their color experience is richer, more detailed. We can't know exactly what they see, just as they can't know exactly what 3-cone vision is like. All of this shows that color vision isn't one standard experience. It's a spectrum. Your brain builds color from whatever signals your cones provide. Whether you have 2 types of working cones, 3 or 4, your brain creates a consistent experience of the world that makes sense to you. The colors you see are unique to your visual system. Someone else looking at the same sunset might be having a slightly different experience. Not worse or better, just different. And yet, somehow, we all navigate the same world, all find beauty in it, all use color to make sense of what we see. Vision adapts. It works with what it has, and it shows each person a version of reality that feels complete. Your eyes change as you move through life. The lens that bends and flexes so easily when you're young gradually becomes less flexible. The proteins inside it become denser. The layers that have been forming since birth make it slightly larger and firmer with each passing year. When you're a child, your lens can change shape dramatically. You can focus on something just inches from your nose. A child reading a book can hold it close, and the lens accommodates easily. But as decades pass, this flexibility slowly decreases. The lens still works, but it can't curve quite as much as it once did. Most people notice this change somewhere in their 40s. Suddenly, reading small print becomes harder. You might hold a menu farther away to see it clearly. Or you find yourself needing more light to read comfortably. This is called presbyopia, which simply means aging eyes. It's not a disease. It's a natural part of how eyes work over time. Reading glasses help by adding extra magnification. They do some of the bending work that your lens can no longer do as strongly. Many people need them eventually. It's just your lens being less flexible after decades of constant adjustment. The same lens that focused perfectly on everything from childhood books to distant stars simply needs a little help with close-up work. Your pupils also change with age. They don't open quite as wide as they did when you were younger. This means less light reaches your retina. Older eyes need more light to see as clearly as younger eyes do. This is why many people prefer brighter lighting for reading as they age. It's not that their vision is failing, it's that less light is getting in. The number of rods and cones in your retina stays relatively stable throughout life, but the connections between them and the nerve cells can become less efficient. Processing visual information might take slightly longer. You might not notice small details quite as quickly, but the fundamental ability to see remains. Your eyes have been working every waking moment of your life. They've tracked countless movements, focused on endless details, adjusted to every lighting condition you've encountered. They've shown you first days of school and graduations, faces of people you love, sunrises and storms, words in thousands of books. The where they show isn't failure, it's evidence of service. Even with these changes, most people maintain good vision throughout their lives. Glasses or contact lenses can correct many age-related changes. And your brain continues to adapt, compensating for small losses in the same way it compensates for your blind spot. You might not see with the same effortless clarity you had at 20, but you still see the world, still experience its beauty, still read and recognize and navigate. Your eyes are faithful companions. They adjust to aging just as your other senses do. They keep working, keep showing you what matters, keep connecting you to the people and places around you. And they do this with a patience built into their very structure, continuing their essential work decade after decade. Even in complete darkness, your eyes don't stop working. They adapt. When you turn off the lights at night, your visual system begins a remarkable transformation that lets you see in conditions that would have seemed impossible moments before. The first change happens quickly. Your pupils open wide, expanding to their maximum size. This lets in as much light as possible. But this is just the beginning. The real adaptation takes longer and goes deeper. Your rod cells start to wake up fully. Remember, rods are your night vision specialists. In bright light, they're overwhelmed and step back, letting your cones do most of the work. But in darkness, rods take over. They begin producing more of the light-sensitive proteins they need to catch even the faintest photons. This process takes about 20 minutes. If you've ever walked into a dark movie theater from bright sunlight, you know this timeline. At first, you can barely see anything. You stumble looking for a seat. But if you wait patiently, the room gradually becomes clearer. Shapes emerge. You can see the outline of seats and people. This is your rods fully adapting to the darkness. Once your eyes are fully dark adapted, they become incredibly sensitive. Your rods can detect a single photon of light. That's the smallest possible unit of light that exists. Think about that scale. Your eyes, these soft biological structures, can catch the tiniest spark in an ocean of darkness. In perfect darkness, after full adaptation, you could theoretically see a candle flame from about 30 miles away. Of course, in the real world, air and terrain get in the way. But this shows just how sensitive your night vision can become. Your rods are that powerful when they're working at their peak. The trade-off is that you lose color vision in the dark. Rods can't detect color. They only register light and dark. This is why everything looks gray at night. The colors are still there, reflecting the same wavelengths they always do. But without enough light to activate your cones, your brain only receives brightness information from your rods. The world becomes a painting in shades of grey. Your night vision is better at the edges of your vision than in the center. Remember, rods are concentrated away from your fovea. This creates an interesting effect. If you want to see something faint in the dark, like a dim star, look slightly to the side of it. You'll see it better with your peripheral vision than with your direct gaze. Ancient sailors and hunters knew this trick long before scientists understood why it worked. Bright light destroys dark adaptation instantly. Turn on a lamp in a dark room, and your pupils shrink. Your rods become overwhelmed again. If you turn the light back off, you have to wait another 20 minutes for full adaptation to return. This is why astronomers use red lights at night. Red light doesn't affect rod sensitivity as much as white light does, so they can read their equipment without losing their night vision. Your eyes are patient in darkness. They wait, adjust, and gradually reveal a world that seemed invisible at first. Humans see the world in one way, but other animals see it completely differently. Each species has evolved eyes that match what they need to survive. And some of these visual systems are remarkably different from ours. Eagles can see about 4 times farther than we can. Their eyes are almost as large as ours, but their bodies are much smaller. This gives them incredibly detailed vision. An eagle soaring a mile high can spot a rabbit on the ground. Their retinas are packed with about 5 times more light-catching cells per square millimeter than human retinas. Every glance captures extraordinary detail. Cats have eyes built for hunting at dawn and dusk. Behind their retina sits a special layer called the tapetum lucidum. This layer acts like a mirror, reflecting light back through the retina a second time. Any photons the rods missed on the first pass get another chance to be caught. This is what makes cats' eyes glow in the dark when light hits them. You're seeing that reflective layer bouncing light back out. This adaptation gives cats vision about 6 times better than ours in low light. Bees see colors we can't imagine. They have photoreceptors that detect ultraviolet light, wavelengths too short for our eyes to catch. Many flowers have ultraviolet patterns invisible to us but vivid to bees. These patterns guide bees to nectar, like runway lights guide planes. A flower that looks plain yellow to you might look like a yellow bloom with purple streaks to a bee. They're seeing a version of the world that exists beyond our visual range. Some deep-sea fish live in near total darkness. Their eyes have evolved to become enormous compared to their body size. A fish, the length of your hand, might have eyes as large as golf balls. These huge eyes collect as much light as possible from the faint glow of bioluminescent creatures in the deep ocean. Some species have tubular eyes that point only upward, watching for silhouettes of prey passing overhead against the slightly lighter water above. Mantis shrimp have, perhaps, the most complex eyes on Earth. They have 16 types of color receptors compared to our 3. They can see ultraviolet light, visible light, and polarized light. Scientists still don't fully understand how their brains process all this information. The mantis shrimp might be seeing colors and visual dimensions we can't even conceive of. Owls have eyes fixed in their sockets. They can't move their eyes the way you can. To look around, they must turn their entire head. Their necks can rotate up to 270 degrees to compensate. But this trade-off gives them something valuable. Their large, forward-facing eyes provide exceptional depth perception and light-gathering ability for hunting at night. Each species sees what it needs to survive. Eagles see distance for hunting from the sky. Cats see in dim light for dawn hunting. Bees see ultraviolet for finding flowers. Deep sea fish see in near darkness. Mantis shrimp see complexity we can barely imagine. And humans see the world with color, detail, and adaptability that serves us perfectly for our way of life. Each eye is a different window into the same physical world. Your eyes communicate even when you're silent. They reveal what you're feeling before you say a word. The muscles around your eyes, the size of your pupils, the direction of your gaze, all of these give away your inner state. When you're genuinely happy, the muscles around your eyes crinkle. These are called crow's feet when they become permanent with age. But they appear temporarily whenever you smile for real. This is why a fake smile looks different from a genuine one. A fake smile uses only the mouth muscles. A real smile reaches the eyes. People can sense this difference, even if they don't consciously know what they're looking for. When something surprises you, your eyes open wider. Your eyelids pull back. Your eyebrows raise. This happens automatically. The wider opening lets in more light, more information, helping you quickly assess whatever unexpected thing just happened. It's your visual system preparing to gather as much data as possible in a moment of uncertainty. Your pupils do something interesting when you're thinking hard. They dilate slightly, opening wider even though the light hasn't changed. Scientists have found that mental effort causes this dilation. The harder the problem you're working on, the wider your pupils become. People playing difficult card games or solving complex math problems show noticeable pupil expansion. Your eyes are literally opening to help your brain work. Pupils also dilate when you see something you like or find interesting. Show someone pictures of things they love, and their pupils will grow larger. This response is unconscious and hard to control. Your eyes reveal your preferences without asking your permission. In fact, researchers have used pupil measurements to study attraction and interest because pupils don't lie the way words sometimes do. When you're tired, your eyelids droop. Blinking becomes slower and longer. Your eyes might feel heavy, fighting to stay open. These signals tell others around you that you need rest. Even animals recognize these signs across species. A person with drooping eyes communicates exhaustion in a universal visual language. Fear changes your eyes too. Your pupils dilate to take in more of a threatening situation. Your eyes widen to increase your field of view. You might stare without blinking, focused entirely on the source of danger. Or your eyes might dart around rapidly, scanning for escape routes. These responses happen faster than thought, driven by ancient survival instincts. Sadness shows in eyes that lose their brightness. The area around the eyes might swell slightly from tears. The gaze might drop downward or become unfocused. Even without crying, sad eyes look different. They carry an expression that others recognize immediately, triggering empathy and concern. All of these signals happen automatically. You don't decide to crinkle your eyes when you're happy or widen them when you're surprised. Your emotional state changes your eyes, and your eyes broadcast that state to everyone around you. It's a communication system older than language. built into the structure of your face and eyes. People read these signals without realizing they're doing it. You can sense someone's mood from their eyes alone, even if their face is partially covered. Eyes are windows, not just for seeing outward, but for feelings showing through. When you look into someone's eyes, something unique happens in your brain. Special neurons fire that only respond to direct eye contact. These cells don't activate when you look at someone's ear or shoulder, only eyes. This is why eye contact feels different from looking at any other part of a person. This connection is powerful. It creates a sense of being seen, truly noticed, that no other form of attention provides. Two people meeting each other's gaze establish a link that feels almost tangible. You can feel when someone is really looking at you versus when their eyes are pointed your way, but their attention is elsewhere. Babies learn early to seek out eyes. A newborn, just days old, will spend more time looking at faces than at any other visual pattern. And within those faces, they focus mostly on the eyes. This is one of the first social skills we develop. Before we can speak, before we can gesture, we can make eye contact. It's built into us as a fundamental way of connecting. Throughout life, eye contact remains essential for communication. It signals attention and respect. When you talk to someone and they meet your eyes, you feel heard. When they look away constantly, you sense disinterest or discomfort. These feelings arise automatically from deep social instincts about what eye contact means. In a conversation, people naturally take turns with eye contact. The speaker looks away occasionally while thinking. The listener maintains more steady eye contact to show they're following along. When the speaker finishes, they look directly at the listener, signaling it's their turn to respond. These patterns happen so smoothly, you rarely notice them, but they structure nearly every face-to-face conversation you have. The length of eye contact matters too. A brief glance acknowledges someone's presence. A longer gaze shows interest or concern. Holding eye contact for too long can become uncomfortable, even threatening. Different cultures have different rules about how much eye contact is appropriate. But all cultures use it as a form of communication. Eye contact can communicate things words cannot. A glance across a crowded room can say, "I see you," or "I need to leave," or "Did you hear that?" Parents and children develop their own language of looks. A warning glance, an encouraging smile caught in a meeting of eyes. Understanding passed in a fraction of a second. There's intimacy in sustained eye contact. Looking into someone's eyes for more than a few seconds creates a feeling of vulnerability and connection. This is why prolonged eye contact often happens between people who are close, people who trust each other. It requires letting someone see you, really see you, without the buffer of looking away. Scientists have found that eye contact synchronizes brain activity between two people. When you look into someone's eyes and they look back, your neural patterns begin to align in measurable ways. You're not just exchanging glances, your brains are coordinating, preparing to understand and connect with each other. In a single look, you can communicate concern, affection, warning, or comfort. You can share a moment of recognition or understanding. Your eyes meeting someone else's creates a bridge between two minds, two inner worlds, touching briefly through vision. Your vision isn't perfect. Your brain fills in gaps, makes assumptions, and takes shortcuts. This is why optical illusions work. They reveal the clever ways your visual system usually helps you, by showing the rare moments when those shortcuts lead you astray. Look at two lines side by side. One has arrow-like marks pointing outward at the ends. The other has marks pointing inward. The lines are exactly the same length, but one looks longer than the other. Your brain interprets the arrows as depth cues, the kind you'd see in corners of rooms. It adjusts what you perceive based on these cues, even though the lines are flat on a page. Some illusions make still images appear to move. Patterns of contrasting colors and shapes can create the sensation of rotation, or waves flowing across a page. Nothing is actually moving, but your eyes make tiny movements called microsaccades. And when these interact with certain patterns, your brain interprets the shifting information as motion. The movement you see is entirely created by your visual system. Colors can fool you too. Place a grey square on a white background and another identical grey square on a black background. The one on white looks darker. The one on black looks lighter. They're reflecting exactly the same wavelengths, but your brain adjusts each color based on its surroundings. Your visual system cares more about relative brightness than absolute measurements. It's trying to figure out what objects really are, not just what light they're reflecting in this particular moment. Some illusions play with your expectations. Show someone an image of a vase, and they might suddenly see two faces in profile looking at each other. The image hasn't changed, but their brain has switched which parts it treats as object and which as background. Your brain constantly makes these decisions about what matters in a scene. Usually, it's consistent. But with carefully designed images, you can flip between two valid interpretations. These tricks aren't failures of your vision. They're side effects of how efficiently your visual system normally works. Your brain needs to process information quickly to help you react to the world. It can't carefully analyze every detail. Instead, it makes educated guesses based on patterns it has learned throughout your life. Most of the time, these guesses are exactly right. When you see a stick partially submerged in water appearing bent, your brain correctly interprets that light bends when passing between water and air. When you see railroad tracks appearing to converge in the distance, your brain correctly uses this perspective to judge depth. Your visual shortcuts usually serve you well. Illusions show you the rules your brain uses by creating situations where those rules give unexpected results. Lines that look bent but are straight. Sizes that seem different but are the same. Motion where there is none. Each illusion is a glimpse into the normally invisible processes that construct your view of the world. Your brain cares more about speed and usefulness than perfect accuracy. It evolved to help you survive and navigate, not to measure everything precisely. And so it builds your visual world from assumptions, context, and quick decisions that are right far more often than they're wrong. When you dream, your eyes move. Close your eyelids right now and move your eyes left and right beneath them. You can feel the movement, even though your eyes are closed. During certain stages of sleep, Your eyes do this on their own, darting back and forth in patterns that seem to follow something only you can see. This stage is called REM sleep. REM stands for rapid eye movement. It happens several times each night, in cycles that get longer as the night progresses. Your first REM period might last only 10 minutes. By morning, you might spend 30 minutes or more in REM sleep before waking. Scientists discovered REM sleep by watching people's closed eyelids while they slept. The eyes beneath would suddenly start moving rapidly, left and right, up and down, as if watching something. When researchers woke people during these periods, they almost always reported dreaming. Wake them during other sleep stages, and they rarely remembered dreams. The connection between eye movement and dreams is fascinating. Some researchers think your eyes might be tracking the action in your dreams, following dream images the way they follow real objects when you're awake. If you dream of watching a tennis match, your eyes might move back and forth. If you dream of climbing stairs, your eyes might move upward. Not everyone agrees this is what's happening. The eye movements might instead be your brain reactivating visual pathways, keeping them active even though no light is entering your eyes. The movements could be a side effect of the neural activity that creates dreams, not a response to dream content. Scientists are still working to understand the exact relationship. What's clear is that your visual cortex, the part of your brain that processes sight, becomes highly active during dreams. Brain scans show this area lighting up almost as much as when you're awake and looking at things. Your brain is generating visual experiences without any input from your eyes. It's creating images, faces, places, colors, all from memory and imagination. This ability is remarkable. Your brain can produce vivid visual experiences entirely on its own. Every dream scene is proof that vision doesn't require eyes to function. Your mind can construct images, can create the sensation of seeing, using only its own internal processes. Some dreams feel incredibly realistic. Colors are vivid. Details are sharp. You can see faces of people you know, or strangers your brain invents. You can read text, though it often changes when you look away and back. Your dreaming brain builds visual worlds that feel as real as waking vision, at least until you wake and realize it was all internal. During REM sleep, your body becomes temporarily paralyzed, except for your eyes and breathing muscles. This paralysis protects you from acting out your dreams, but your eyes remain free to move, darting beneath your closed lids, following visions that exist only in your sleeping mind. Right now, as you prepare for sleep, your eyes will soon close for the night. They'll rest in darkness, and then, hours from now, they'll begin to move again, tracking dreams through the private theater of your sleeping mind. Close your eyes for a moment. Now, picture a beach, the sand under your feet, the waves rolling in, the sun warming your skin. You can see it, can't you? Not with your eyes, but in your mind. This ability to create mental images is called visualization, and it uses the same parts of your brain that process real vision. When you imagine a scene, your visual cortex activates. Brain scans show this clearly. The areas that light up when you look at a real beach also light up when you imagine one. Your brain treats mental images almost like real ones, processing them through similar pathways, creating similar neural patterns. Some people see mental images vividly, almost like photographs. Ask them to picture their childhood bedroom, and they see it in detail. The color of the walls, the pattern on the bedspread, the way light came through the window. For them, visualization is nearly as clear as seeing with open eyes. Others see mental images more dimly. The pictures are vague, lacking detail. They know what their bedroom looked like. They can describe it, but they don't see a clear image. They experience memory more as concepts and descriptions than as visual replays. A small percentage of people have no visual imagery at all. This condition is called aphantasia. When asked to picture something, they experience nothing visual. Their mind stays dark, but they can still remember facts about things, still describe them, still navigate the world perfectly well. Their memory just works differently, without the visual component many people take for granted. Most people fall somewhere in the middle. You can probably picture familiar faces, remember what your home looks like, imagine future events in your mind. These mental images might not be perfectly clear, but they're present enough to be useful. Your mind's eye helps you in countless ways. When you follow directions, you might visualize the route. When you remember the past, you might see scenes play out in your mind. When you plan the future, you might picture how things will look. This internal vision shapes your thoughts and decisions, even though you're not always aware of it. Athletes use visualization deliberately. They imagine performing their sport perfectly, picturing each movement in detail. Studies show this mental practice can actually improve physical performance. Your brain rehearses the actions even without your body moving. The neural pathways strengthen just from the visualization. You can also visualize things that don't exist. Fantasy scenes, impossible objects, creatures no one has ever seen. Your mind can take elements from reality and recombine them into something entirely new. Every fictional character you've imagined, every invention you've dreamed up, started as mental images created by your visual cortex, working without input from your eyes. This ability bridges memory and imagination. You can recall the past visually and project yourself into possible futures. You can rotate objects in your mind, see them from different angles without touching them. You can plan how furniture will fit in a room before moving anything. Your mind's eye is a tool for thinking, planning, and creating. It's vision turned inward, showing you images from memory and imagination instead of light from the world you've been seeing all your life. Light enters your eyes, cells respond, nerves carry signals, your brain creates meaning, and somehow, through this biological process, you experience the beauty of the world around you. Think about what your eyes have shown you. The first faces you ever saw. Sunrises that painted the sky in colors you couldn't name yet. Words that taught you everything you know. The expressions of people you love. Mountains and oceans and city streets. Every book you've read. Every screen you've watched. Every path you've walked. All of it came to you through these two small organs that never stop working. Your vision connects you to everything beyond yourself. It lets you recognize faces across a crowded room, navigate through spaces without touching every surface. Learn from the experiences others have written down. See beauty in a sunset, or a painting, or a simple flower growing in a crack in the sidewalk. The system that makes this possible is intricate. Lenses that focus, retinas that catch light, nerves that carry messages faster than you can think, a brain that fills in gaps, corrects for errors, and builds a complete world from incomplete information. Rods and cones working together to show you brightness and color. Pupils adjusting thousands of times a day to let in just the right amount of light. And through it all, you simply see. You don't have to understand the process. You don't have to consciously control any of it. Your visual system works quietly, faithfully, showing you the world moment by moment, day after day, year after year. As you prepare for sleep now, your eyes will finally rest. The constant adjustments will slow. The information flowing to your brain will decrease. Your eyelids will close, and for hours, your eyes will be still, except for the gentle movements of dreams. But tomorrow, when you wake, they'll open again. Your pupils will adjust to the morning light. Your lens will focus. Your rods and cones will begin catching photons. And you'll see another day, another collection of moments, more faces, more colors, more of this world that your eyes work so hard to show you. Your vision is a gift that's easy to take for granted because it's always there. But tonight, as you close your eyes, you can appreciate it. The quiet miracle that's been happening since you first opened your eyes as a newborn. The faithful work of cells and nerves and brain regions all cooperating to give you sight. If this journey through the science of vision brought you peace tonight, we'd love for you to subscribe. Tomorrow we'll explore something equally amazing together. And leave a comment below. What fact about vision surprised you most? Where are you watching from? And what time is it there? We love hearing from you. Until then, rest well. Let your eyes close gently. They've worked hard today, showing you everything from your first glance this morning to these final